All right, good morning everybody. Let's get started. So on Monday we discussed about simplification of the BJT model using various techniques depending on the situation, like the hybrid pi model and a few other models like that. And also we looked at how to represent an NPN and PNP transistor models. We said they are pretty much the same. You don't have to do anything. It's the same model, except that for PNP transistors, currents and voltages need to be reversed. So if you just assume it's a NPN transistor and draw the equivalent circuit, the currents and voltages will be negative. That's all that will happen. So it was clear. And then we also looked at few low frequency MOSFET small signal models, right? And in addition, so basically the model that we used was switched current source model in parallel with a output resistance, right? So we said we will be using an output resistance in parallel in small signal analysis. We also looked at a special case where ground, the gate is short circuited to the drain, and we said that under such situations, when for a MOSFET, if you short circuit the ground to the drain, it behaves like a resistor, and this is basically what is used inside ICs. Right. So fabrication is much easier to implement a MOSFET and short circuit the drain and gate than to implement a resistor. So therefore, that's where we stopped last Monday. Any questions up to now from this? No? Okay. So what we are going to do today is basically discuss how to solve a problem, a typical problem like what you would get in the exam. Now, I have discussed one such example and posted the video. Hopefully, you have watched it. It's on BJT small signal model analysis. So, I am not going to discuss that again here. It will be pretty much the same. So, instead I will be discussing a different problem, which will be for the MOSFET, the small signal analysis for a MOSFET circuit. Okay. All right. So, I have asked in a WhatsApp group, I have sent a message asking you to try the example 7.3 in Sedra and Smith textbook. How many of you have tried it? And you don't have to have correctly done it, but at least tried. One, only one, two, okay, maybe a couple of people have tried. And now the important thing is about problem solving is when you see someone solve a problem, it looks like it's trivial, right? You could do it easily. But when it comes to actually, when you see a problem for the first time, especially in the exam, you wouldn't feel like that. In order to actually be able to answer a problem, you should have some practice. So therefore, I highly encourage that you try some examples before you go to the exam, right? So we'll do this first. Okay. So we have a problem like this. So MOSFET circuit. Simple MOSFET circuit, but this is a little bit different from what you have been doing, looking at. So here what you have, the biasing is done slightly differently, and this is a circuit that you have. So voltage VDD is 15 volts, RD is 10K, load resistor RL is also 10K. This biasing resistor, remember, all what you need is a voltage. You don't need to provide a big current, because there is, because of this oxide layer here for the MOSFET, no current flows, right? So therefore, all what we put is a very big resistor, 2 mega ohms. Sorry, 10 mega ohms resistor. This is RG. This RG, 10 mega ohms. And the input is provided from here. This is the input voltage provided here. And these capacitors are considered large capacitors, so that they can be considered as short circuits when it comes to the AC analysis, right? And open circuit for DC, right? So this is biased with drain to gate. So biased with drain to gate resistor, RG. So the purpose of RG is biasing, so that the gate is above more than VT, so that it operates in the saturation regime, and capacitors are large. So the capacitors are large. So what we need to do is find one small signal voltage gain to input impedance and 3 largest allowable input voltage, input signal, so that it operates within the saturation region, so that we can use it as an amplifier, right? So those are the 3 things that we need to do. What is the input impedance? Rin is basically the impedance looking into this terminal between ground and gate. And right, so that's basically, and what is the biggest value of Vi? That ensures this will still operate within the saturation region. That's the last question, right? So that's basically those are the 3 things that we need to do. Now, before we actually find the small signal voltage gain, we need to ensure that this actually operates in the saturation region. We need to check that, right? So to do that, we need to go, so that is ensured in the DC biasing. It has to be properly biased. So the first step is step 1, DC analysis. Why? We want to find the operating point and ensure that VGS is greater than VT, V threshold, and VDS is greater than the overdrive voltage, which is VGS minus VT, right? So that we need to ensure. Okay, so if we find the values, and here we have some values given. So the values given here are VT threshold voltage is given to be 1.5 volts. K value in the current equation is 0.25. milliamperes per voltage squared. And R naught, the output resistance, the equation for R naught in general, this is not just for this equation, you can, we showed this last time I think, this has to be VA divided by I, quiescent current, DC current, DS quiescent current, right. And VA is also given, let me write it here, VA is equal to 50 volts. So, these equations are given. So, the first thing is basically doing the DC analysis. For that, we first draw the, so determine DC operating point. So, in order to do that, first we draw the DC circuit. Draw the DC circuit. How do we obtain the DC circuit from this? You at DC, you know capacitors are open circuited. If you have any inductors, you short circuit, right? So, short circuit capacitors and open circuit inductors. So, we can draw it. We have the DC source, resistor, and that's all you have. No other components are there. This side is open circuited, so this side is not there. This side is open circuit, that side is not there. So, that's basically what you have, where this is the gate, this is the drain, and this is the source. And this voltage is VDD, 15 volts. You have IDS, these are all capital because these are the, yes. Sorry? Say that again.
For DC analysis, capacitors open circuit.
Yes, capacitors are open circuit. You don't have any capacitors here.
Short circuit capacitors.
No, you short circuit capacitors for AC analysis, because DC, for DC analysis, the impedance of a capacitor is 1 over 2 pi Fc. So, when F is equal to 0, DC is F equal to 0. So, this becomes infinity. So, that becomes, sorry, this becomes 0, this becomes infinity at DC. So, open circuit means you disconnect. Okay? Is it still correct? Yeah. Here? This side? Okay, thank you. Now only I understood what the question was. Right, thank you. So, for both of you, for clarification, I will give points. This is open circuit capacitors and short circuit inductors. Very good, thank you very much. Thank you very much. Right, good. So, you guys are awake. I am asleep. Right. So, this is basically IDS. These are capital letters, meaning that they are DC currents. So, you have RD 10K, RG 1M, sorry 10M, 10 mega ohms. Current IG is 0. The voltage here is VGS. The voltage here is VDS. So, it is a matter of finding IDS, VDS and VGS, so that we can compare those values, right. We know that IG is equal to 0 because it goes into a kind of oxide layer, so large input impedance. So, therefore, the voltage, since this current is 0, the voltage across this Ig Rg is equal to 0. If that is the case, this voltage is the same as this voltage. So, therefore, Vd is the same as Vg. In other words, Vds is equal to Vgs. What that means is this voltage is the same as this voltage under this condition. Clear? Vds is the same as Vgs because there is no current flow through this. Now, if this is in saturation, right, assume this is in saturation. If that is not, later on something nonsensical will appear, right. So, we will try that. In saturation, IDS is K divided by 2 Vgs minus Vt squared. This is all again DC quantities. Let us call this equation number 1. So, if I apply the Kirchhoff's voltage law to this circuit, VDD minus IDRD is equal to VDS, right. Apply KVL to output loop, that I will get VDD is equal to VDS plus IDS RD. That is number 2. So, if I apply ID from there, I get VDD is equal to VDS plus IDS is this, but VGS is equal to VDS, right. So, therefore, this is also equal to K divided by 2 VDS minus Vt squared from here, right, from here. That is why I put it there, okay. I have replaced this with ID is K divided by 2 VDS minus Vt squared. Now, this is just a equation of ds, right. So, I can expand this and write it like, so you have here VDS squared. So, K divided by 2 and there is the RD also. K divided by 2 RD VDS squared, and VDS terms I have 1 plus K divided by 2 RD times, now when you have the internal term, you will have 2 VDS Vt negative, right. So, you have a negative, you have 2 this term times Vt term. Yes, okay. So, this cancels. So, let me write this as 1 minus K RD Vt times VDS plus this term here plus this. You have K divided by 2 RD times Vt squared, and then this VDD. So, I have taken it to this side, that whole thing should be equal to 0. Okay. So, if you substitute values for K, RD, V and Vt, right, K is 0.25 milliamperes per volt squared, Rd is 10K. So, if you apply that, you will get 1.25 VDS squared minus, if you apply all this, you will get 2.75 VDS minus 12.1875 equals to 0. That is the quadratic equation that you get. It is a matter of now our aim is to find VDS and IDS, the operating point. So, if you know this, VDS should be equal to minus B, that is, this is B. So, A is 1.25, B is minus 2.75, C is minus 12.1875, right. So, minus B that is 2.75 plus or minus square root. Inside the square root we have B squared 2.75 squared minus, but there is another minus, so this becomes plus 4 times A 1.25 times C 12.1875. The whole thing square root divided by 2A. 2 times A is 2.5, right, 2 times 1.25. So, VDS, the values, so you put the things in and see, obviously this what is inside this is bigger than 2.75, 2.75 plus something is there, right. So, therefore, if you take the negative sign here, 2.75 minus something bigger than 2.75, that will become negative, right. You can't have a negative VDS for this setup, okay. It has to be positive, at least to be in the saturation it has to be positive, plus you only have a positive supply. So, anyways you can't have a negative value. So, right, the two values that you get are 2 points, so the VDS is equal to either 4.41 volts or minus 2.21. Obviously, VDS is greater than 0, therefore, VDS has to be 4.41 volts. That is the correct answer. That is the operating point voltage in order for it to be in the saturation. Now, if that is the case, we know that VGS is also equal to VDS, that is equal to 4.41. Now, if this is to be in saturation, VGS has to be greater than VT. VGS is what? 4.41, which is greater than 1.5. So, therefore, that is satisfied. VDS has to be greater than or equal to V overdrive, which is VGS minus VT. VGS is 4.41, VT is 1.5, so that will give me 2.9. Now, if VDS is greater than that, that should be fine. So, we know 4.41 is greater than that, right. So, therefore, that condition is also satisfied. That is also satisfied. Therefore, we verify that my amplifier is in fact in saturation operation, right. Therefore, operating in saturation mode. Okay. So, we know the Q point. This voltage is 4.41 volts, which is the same as this. If you want, you can find the ID also. IDS is equal to this equation you applied. So, VGS minus VT is 2.9, 2.9 squared times this, you will have this equal to 1.06 milliamperes, right. So, this current IDS is 1.06 roughly 1 milliampere, right. So, you can assume that to be 1 milliampere roughly. Clear? This analysis simple, right. Right. Let us leave this side alone and then work here. So, now the small signal analysis. Now that we have verified it is in active region, we now go to small signal analysis. Again we do the same thing, draw the AC equivalent circuit. You do the AC equivalent, and now you do short circuit capacitors, open circuit inductors, and replace voltage sources these are independent voltage sources with their R source resistances, in other words short circuit voltage sources, because it does not have any output impedance, almost 0, right. And similarly, if you have any current sources, open circuit current sources, or replace with RS. Okay, so that is basically what you would do. So, if you do that, the circuit that you get, so let us first draw the transistor. You have a gate, you have a drain, and you have a source. So this is the drain, source, and gate. So between drain and source you have a you have this dependent voltage source. This one is open circuit, and in addition you also have in this model a small resistor, you have a resistor R naught. This is the right. So you have this as the transistor. This value here is Gm times V, simple VGS, right. These are all simple values, or else you can put phasors, right. You can put phasor values, capital V simple GS, or so these are phasors, okay. That means phasor values. Either you can use that, or even simple G is fine, in which case it is the AC plus AC component only. This is only the AC component. Let's put this simple value, otherwise we might get confused. I might switch these things. So let's put it as simple V so that it is clear. It is the AC value. You can typically put either this or capital V simple GS, right? The phase, either way is fine. Right. So this is the transistor. Between the drain and the VCC, which is short circuited to the ground. So therefore, between the drain and ground, you have RD. Between the drain and source is grounded. Source is grounded here. Between drain and ground, you have RD. You have a capacitor from drain to this circuit, which is short circuited now, and from that there is another resistor. So therefore, RL is also there. If you look at this side, you have a resistor from gate to drain. So gate to drain, you have a resistor. So you can put it so this is gate, right? So you can put it. So that's the gate. So you have the gate, and from there you have the input voltage. So my circuit is, this is my MOSFET. This is the MOSFET. Okay. This is the gate. Correct? And here you have the input voltage V in. Like that. It's VI. VGS. VDS, which is also equal to the V out. This is ID, S. This let's call I in. So the current that is coming here does not go into this. So the whole current goes through this. This is I in. So this is I in. Okay. The same current has to go through only that resistor. Right. So we know a relationship between ID and VGS, ID and VDS, but VDS is the same as VGS. So therefore, wherever you have VDS, we can replace it with VGS. But that is only for DC. But here if you look at this, D and G, there is a resistor in between and there is a current. So therefore, AC currents, the AC voltages, V simple GS and V capital DS are not the same. There is a voltage difference, right? But the capital VDS and capital VGS, or the DC components, are the same. Okay? So we need to keep that in mind. We know the relationship between this this is AC plus DC. That we know. and that basically gives you a relationship between VGS, IDS. What does it look like? Up to VT there is nothing, 0. From there on you have a quadratic relationship between that voltage, which is basically, if you draw a axis here, whatever the voltage here is the V overdrive. VGS above VT is the V overdrive, right? So that's a quadratic relationship. So that's basically the equation that is governed by this from here on. Not for the cutoff, but for the saturation. Okay? So it looks like that. So this is VT. Any voltage from here on is V overdrive. That is VGS minus VT. Now, for this we know the operating point. Let's say our operating point is somewhere here, which is VGS IDS. That's the Q point. And what is this slope? This is basically the input, this is the output. The slope is the gain. If you look at this, input is VGS, output is IDS, that current. So this slope of this is actually the VGM, sorry, GM. GM is the slope, right? So what you have here, if you draw a line like this through that, this specifies the relationship between these two, because what you have here is two axes here. This is V simple GS, this is IDS. Okay? So that's your small signal. So you have the DC and AC together, DC operating point and small signal axis. And the relationship between the small signals VGS and IGS is this blue curve, which is characterized by, we derived it last time, right, by differentiating and multiplying by VGS, right. So this relationship is, so IDS is equal to GM VDS, where GM is basically the differential of this thing at IDS over dVGS at VGS is equal to VGS at that point. Slope at that point. Obviously, if you change this location here, it's going to have a different slope, so different GM, right. So we are only looking at the GM at this operating point, only around that small area, right. So this is that. So it's easy to differentiate this. So 2 times K divided by 2 VGS minus VT is the thing, and when you substitute, so this will be 2 times K divided by 2 VGS minus VT at VGS is equal to VGS. So when you apply this VGS here, you will have GM is equal to K V capital GS minus VT. That's your slope. This is the overdrive, right? This is the K times V overdrive at DC. That is 2.9 volts that we calculated earlier. V overdrive is 2.9 times 0.25. That gives me this value equal to 0.725 milliamperes per volt. Milliamperes per volt. This is 1 over resistor, 1 over ohm. So That also, this value we now have. In addition to that, we are also given R naught, which is VA divided by IDS, which is equal to 50 divided by 1 milliampere. 1.06 is roughly equal to that, which is equal to 50. Let's, if you can get it as 50 or 1.06, if you use 50 is equally valid, okay. 47 kilo ohms. 47 kilo ohms. If you want to say it's roughly equal to 50, that is fine. Because assuming this to be roughly 1. Okay. Now we have these quantities. You have this, you know this, you know this, you know this value, and you know this value, right? So let us observe that all three resistors here are in parallel. So we can lump them together in a single resistor, right? So here this is between DNS, 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 right? So we can put them together. So we can redraw this circuit as like this. So you have the MOSFET between drain and source, and then there is this single resistor R whose value is RD parallel RL parallel R naught. And then you have a resistor between the drain and the gate, which is RG. And then you have the VI. Okay, so that's basically what you have in here. Input current is I in. Input voltage is VGS. And this one is GM times VGS. And this current is different from what you have here, right? This is a different current. Let me call this I. It's not I load, it's some other current I. So you have this circuit like that. This is the gate, drain and source, grounded. So if I apply Kirchhoff's voltage law to output load, this loop, I get VDS is equal to minus I times R. But I is I in plus GMVAS, right? So this is minus GM VGS, that's this current, plus I in. I have written minus I in, but it should be plus I in, right? No, sorry, this is wrong. The I times R. So I is this current minus that. So what is going on is, if you apply the Kirchhoff's current law there, I in plus I minus VGMGS will be equal to 0. So therefore this current is GMVGS minus I in. Right, now it's correct. Okay. So what I am interested about is this, not this one. This plus this is equal to that. So therefore this is equal to this minus that. Sorry, this is equal to this minus that, right. So you have that times R. R is this thing here, okay. R, this value is basically 10K parallel 10K parallel 50K If you want, so you know this, the parallel combination of this and this is 5K. It should be somewhere around 5, but if you calculate this, R value will be equal to 4.5K. Okay, if you want to keep that 0.5, can do that, right? So 4.5K is the value for R. So this is 4.5K. GM is basically 0.725. VGS is basically the value that we want. So you have this. But I in from this, that is this voltage, it's basically this voltage difference divided by RG. Okay. So this voltage minus this voltage divided by RG is equal to I in, right? I in is equal to VGS minus VDS divided by RG. Therefore, I can substitute I in here using this expression. I will get VDS is equal to R VGS, this is the second term, GS minus VDS, this is I in. This is I in minus GM VGS. I have taken this negative sign inside, so that this becomes I in minus GM minus VGS, right? So that's what I have over there. But we know V out is equal to VDS and V in is equal to VGS. But what is AV? So therefore, this should be that term divided by VGS. So I can rewrite this as V out is equal to R V in minus V out over RG minus GM V in times R, right. So if I take this side, rearrange the terms, I will have V out 1 plus this term 1 over RG is equal to V in R over RG, this term, minus GM times R. So therefore, I can get an expression for AV, V out over V in, which is equal to R over RG minus RGM divided by 1 plus R over R, 1 over RG. That is my AV. But noting that, what is the value of R? 5K. What is the value of RG? 10 mega ohms. 10 mega ohms. 10 mega ohms, 5 over 10 mega ohms, almost 0, right? So therefore, this term almost becomes 0, this term almost becomes 0, this becomes roughly equal to negative GM times R. So if you substitute the values, this value will be minus 3.3. So AV, small signal voltage AV is equal to minus 3.3. So that's done. Okay, not hard, right? No, everything was very simple. Right, now the second part is the input impedance. Let's tackle the input impedance. Let's first define what is input impedance. To find that, input impedance R in is defined as V out over V in. V out over V in. Sorry, V out in what am I writing? V in over I in. The voltage divided by current. V voltage is equal to IR, right? So therefore, at the input, this ratio is what you have, but I in we have already seen that it is equal to VGS minus VDS divided by RG. But VDS we have already seen that is equal to AV times VGS, simple GS, right? So this is basically what we did here, right? So right here from this relationship. So you have that because VGS is the V in, VDS is the V out, VDS V in, V out, right? So that's the same thing. So I in is equal to VGS minus VDS, which is basically that AV VGS divided by RG. So if you substitute this VGS 1 minus this one is minus GM R. Okay. So therefore, that becomes plus GM R because AV is equal to minus GM R divided by RG. So therefore, I in V in ratio VGS divided by, so V in divided by I in is equal to RG divided by 1 plus GMR. If you apply the values, this is 4.5, this is GM is point, we calculated that earlier, 0.725. So this value is 10 mega ohms divided by 1 plus 0.725 times 4.5. So this value R in is equal to 2.35 mega ohms. Now, in order to find the largest largest input voltage, right? In order to find, now we have to find the largest input voltage so that it still remains in the saturation region. Now, for this what we use point VI max. For the MOSFET to still operate within saturation region. That means we have to satisfy two conditions, right? VGS, this is AC plus DC, is greater than VT. Let's call this A. And B, the overdrive voltage VDS should be greater than or equal to V overdrive, which is equal to VGS simple. V simple plus capital, right? Minus VT. Those are the two conditions that we need to satisfy. Now, if you remember, we looked at a characteristic curve like this, input versus output voltage characteristic. Remember, what is the input voltage? VGS. Output voltage is VDS. What did it look like? For this circuit, this is AC plus DC. VDS is basically VDD minus IDRD, right? VDS is that. So, up to VT, there is no current. ID is 0. So, therefore, this is at cutoff. My output is at VDD. Remember that, right? So, that's the cutoff. That's up to this point, which is my A. That's the point A. That's the in order for it to be in saturation, it has the VGS has to be greater than VT. That's the point A. That's point A. And after that, the curve goes through the V overdrive squared, VDS minus VDS is equal to VDD minus IDRD, and ID is related to square of the V overdrive. And what is overdrive? The voltage from here on is the overdrive. So, therefore, this section is something like 1 minus squared, right. So, therefore, it goes like a quadratic equation, and then after a while it goes into triode region. So, in the triode region, it will something like this will happen. Now, the question is how to find this point B, that is the border between saturation and triode. Okay. So, if you remember, that is basically overdrive voltage. So, this is the overdrive voltage, right. So, if you draw like this is VDS, this is V overdrive. If I draw this curve, VDS equals V overdrive. So, at saturation triode margin, this has to be equal, right. At saturation triode margin, VDS equals V overdrive, which is basically nothing but VGS minus VT. That is basically this angle. So, in other words, this equation is nothing but, if I draw a 45-degree angle here, that is basically VDS equals to V overdrive, correct. So, therefore, B must be there. B must be at this point. So, therefore, the B point is this. That is my B. But we also know if I draw my operating point, where does my operating point says? VGS equals VDS, right. So, if I draw the VDS equal to VGS, this is VGS equals VDS curve. Operating point has to be there, because at DC there is no current through RG. So, therefore, this voltage is equal to this voltage, VDS equal to VGS, right. So, therefore, that has to be my operating point. Q point, isn't it? So, I can mark the points here. This value is VGS, this value is VDS capital, right. So, now when I input a signal, so what are my simple VDS and VGS? So, my simple values are here. Isn't it? On the operating point, if I draw, this will be my AC operating point, AC axis will be there. So, if I want to now find the input voltage, that is VGS, change in VGS, that puts it into triode saturation margin. How much should I input? That should be on this up to this level, right, isn't it? This is my, so that voltage. So, I have to input a voltage which is equal to this much, isn't it? If I input in this side, if I increase the VG, when it is in the operating point, if I add another, let us call this X amount of voltage, it is going to marginally get into triode region, but still operates in the saturation, because it is the region margin, right, equal sign, right. On the other side, if I reduce this a little bit, that is also possible. You can reduce it so that it goes into cutoff. So, it should be whatever is that or this, let us call this Z, let us call this Z, right. So, if Z is bigger, I have to go with X, that is the maximum, otherwise it will go into triode before it goes to cutoff. If Z is smaller than X, then I have to go with that Z, because it will go into cutoff before it goes. So, for example, it operates right here, then with a small input it will go into cutoff rather than triode, right. So, we need to find this and that, right. So, that is basically what we are trying to do now. So, now most of the time this is easy to find, because then we know VDS is this, VGS is VT, and we can find the difference. Z is very easily found, right. So, Z is basically this voltage difference, that is VGS capital minus VT, that is easy. We know VGS value, we know VT value, 4.5 minus 4.4 minus 2.9, this value is equal to some, I think it is, this is the overdrive voltage, yeah, sorry, this voltage is minus VT, this is the overdrive voltage, V overdrive, VT is 1.5, sorry, this is 2.9 volts, right. So, Z is 2.9, that is easy. Now, if X is smaller than that, this is irrelevant, right. So, now let us try to find X. Now, at that point, at this point, I have the largest VG. VGS cannot go more than that. So, therefore, this point is VGS maximum. Let us put it as capital, because this is just one value. It is not DC, but it is a constant, right. It is not a DC value, but it is not a variable, it is just a maximum value. So, I am going to put a DC value there, right. So, similarly, this one VDS will not come down more than that. So, therefore, this is the minimum value of VDS, right. So, this value V, capital V, this is a constant value VDS min. This is the minimum value. You can't have any VDS value in saturation below this. So, therefore, at this particular point B, at B, I can say VDS min, that is this value, should be equal to VGS max, that is this value, minus VT. This is from VDS equal to VGS minus VT equation, right, because this is the saturation margin, because this otherwise this should have been greater than or equal to, but this operates exactly at that point now, because it is on B, right. So, therefore, that is why this is equal, otherwise it should have been inequality sign, greater than or equal, but I am operating at the equal sign now. So, therefore, this equation holds, this expression is correct. What is VGS max? VGS max is equal to operating point plus x, right, VGS plus the small amount x, that is what we want to find out. So, therefore, VGS max is, I will write it here again, VGS max is equal to VGS plus simple x. Similarly, we can write VDS min, looking at this axis, is equal to VDS operating point minus this amount. Let us call this amount y. Let us call this amount y, okay, VDS minus y. But we know VDS is the same as VGS, that is the DC quantity, right. So, which is equal to, this is equal to VGS. So, therefore, this is equal to VGS minus y. But what is y over x? That is the slope of that blue curve. This is the slope of that the yellow curve. Not this yellow curve, sorry, that is this one. So, this is the operating point. So, if I draw, so not this, let's draw it in a different color. So, if I draw a slope here like that through that operating point, that's the curve that defines VGS to VDS relationship, correct? That is the gain. So, therefore, the slope of this is what defines its gain, right. So, therefore, this is equal to AV, voltage gain. Voltage gain is what? This is VDS divided by VGS. Obviously, this is a negative value, but what I am interested about is the x divided by y, not whether not the direction of it, right. So, therefore, what this is that AV. We know that AV value is equal to GM times something that we calculated earlier, right, R times GM, something like that. So, therefore, from this I can obtain another equation like this, right. So, then what we will have is VGS minus Y, that is this is minus Y, which is equal to VGS minus Y is AV times X. AV times X. This is also equal to VDS mean from this expression, right? That, this, and that. Yeah. So you have this. So therefore, I can write from 1 and 2, because there's 1, the expression for B, this is 1, and 2 is this, 1 and 2. Using these two expressions, and if I replace, if I use this expression, VGS VDS mean is equal to VGS minus AV times X. That is equal to VGS minus that. Is also equal to, from 1, VDS mean is equal to VGS max minus VT, right? Is equal to VGS max is VGS plus X. This VGS max minus VT. Right, so this is okay. So therefore, I can now get rid of these terms, and now that leaves us an expression AV, X and VT. So now I can write it down as X is equal to, so sorry, VT is equal to, you have to take it to this side, VT this side and this that side, VT is equal to X plus AV X. So therefore, X is equal to VT divided by 1 plus absolute value of AV, right? So let's find out that value, because that is important. If it is less than 2.9 volts, we need to go with this, because Z is 2.9, whatever is the smaller one we have to go with. So let's write it again, VT divided by 1 plus AV. We know all these values. VT is 1.5, 1 plus 3.3. So X is equal to 1.5 divided by 4.3. This value comes to be about 0.35 volts. Is less than Z, which is 2.9 volts. Therefore, V in maximum input voltage should be minimum of X and Y, whatever is the smaller one, otherwise it will go into triode region, right? So therefore, when you have that, so therefore this value should be 0.35 volts. 350 millivolts. So the answer to the question here is 0.35 volts. Okay, so we solved everything. Now let's see. Now we assumed linearity, no? In order to assume linearity, you have to operate on this red curve. So if it goes, obviously if you chose, if the value was 2.9, then when I operate here, then there is a big error between the red curve and the orange curve. Yeah. So in that case, our calculations are correct, but the amplifier may not work as a linear amplifier. The non-linearity effects are much bigger then. But with 0.35, since 0.35 is much smaller than the DC voltage, right? Overdrive voltage. But what is overdrive voltage? Sorry. So since X is 0.35 volts, is much smaller than, so it has to be within this region. So I don't know, maybe smaller than VGS, maybe GS. We can assume linearly within the for the amplifier. So let me zoom this in, right? Zoom this in. Let me zoom it in a little bit so that we'll see what is happening there. So what you will have is something like this. So let's have a look at this closely. This is the Q point, and my straight line goes like this. Right, so this is my straight line. This passes through my Q point. So if I move it along this, and after that this will come like that, right? So what I am telling is, if I move 0.35 this way or that, then these points will be roughly here and here. Now the error here, there will be an error. Error will be this much. This will be my error. That is out of linearity. Similarly, from here to here, this will be my error. If it has to be linear, it should be on this red curve. But it is on the yellow curve. Because of that, there is a small error. But what we say is, because this is too small, we can assume this is almost linear. Okay, so this yellow curve between those 2 points are almost linear. That's what we say. Okay, so we ensured that our amplifier actually operates as a linear amplifier. Okay, so that's basically it for the problem solution. Is it clear now? Any questions? You may ask any questions before wind up for today. Questions? No questions. Great. So, so we'll move to a different section on Monday, that is on multi-stage amplifiers. We'll do the lectures as usual on Monday as well as on Friday, and you will have lab classes on Wednesday and Friday as well. Today also in the evening we have lab classes, right? Okay. Any questions about that? Right. So if that is all we need to talk about, let's wind up the class. Thank you.